Swayam Prabha. Digital India. Educated India.
Hello everyone. So in the last week we looked at the absorption in lower dimensional semiconductors, especially the quantum wells. All right. So this week or this lecture I want to introduce selection rules, which are very, very important in understanding the optical properties of semiconductors. And so for that I'll go back to this problem that I talked about. So particle in a box problem, wherein if you confine an electron to a potential well like this, you have these discrete energy levels, right? So these are essentially states that can exist. Now the question we want to ask is, can an electron make a transition from n equal to 1 level to n equal to 2? Can it make a transition from 1 to 3, 1 to 4? So I mean, there are two rules, right? There is this conservation of momentum, conservation of energy. If you look at the conservation of energy, if you shine a photon of, let's say, the energy equal to E2 minus E1, then definitely this should obey. All right. Momentum also should not be a problem because the quantum well is very, very small, right? So it essentially should be able to absorb. The momentum conservation also should be satisfied. But then there is one more roadblock there. That is that is what we call as a matrix element, right? So basically, if you look at the Fermi's golden rule, we have the absorption or emission. The probability of that will depend on the matrix element times the density of states. Okay. So we'll have to understand this a little bit more of detail. Okay. That's what we will try to do in this week. Okay. Similarly, if I take an electron, of a photon which is of energy, E4 minus E1, will it get absorbed? Okay. These are the questions we'll answer. All right. So we'll go back to this, the matrix element, which we said is represented by this. I didn't still correct it. So this is going to be psi f and psi I. So initial and final state wave functions. And then what will happen to the matrix element. Okay. We'll also talk about what is matrix element and why we call it a matrix element towards the end of this lecture. All right. So as you see, the wave function has to be, we have to talk of what is wave function, and we already did that in some way. In the previous lecture, we talked about the plane wave, and then there is the component, the separation of variables that we can do. So there will be a wave function associated with the plane wave component, and then there is this quantized or quantized wave function, right? Phi n is what we called it. So this time I'll try to elaborate that a little bit more. Okay. So what happens is I can't simply take a plane wave because electrons are not simply going to transmit all over the lattice. It's not free space, but there is this lattice potential, because of which there is a block component that comes into the wave function. All right. So I'll say my initial wave function, let's say I'm considering an absorption process, initial wave function is going to be from the valence band. So I'll simply say there is some coefficient AV, which is just a coefficient of normalization coefficient. And then there is going to be a block function U of valence band, UV of R. Okay. So basically there's periodicity that comes in because of the lattice. And then there is this exponential IKR. This is electron can move about in the plane. So in the previous lecture, I just did not mention this part, but it should be there, because if it was only free space, only this, but then electron is actually moving in a lattice. That's why we have to consider this as well. And then of course there is this phi n of Z. So there is an electron in the valence band. So rather, I can represent it phi n. Similarly, I can talk of a psi f, final wave function, which is now, let's say, is conduction band, and there is an envelope function associated with that, exponential IKR. This is wave vector because x and y anywhere it can be, and let's now call it a phi n prime Z. There are these two wave functions that are there, psi f and psi. And we know already, let's say if I take a x electric field in the x direction, the Hamiltonian is going to be E times charge x, right? E naught, right? P dot E is what we said. So Ex E naught is what is going to be, right? So now what happens? We'll have to substitute and we'll get matrix element. But it turns out that now there are two components to the matrix element. Okay. So the M is going to be, you put in psi f and psi I. So there's going to be one component which is basically the dipole moment associated with the valence and the conduction band. So Vc, I'll call it. And then there is an overlap integral m n n prime. That's what. There are two parts. I'll show you what they are in a moment. Okay. So now my confinement is in the z direction. And if you put this in, basically this is d cube. So d cube means this is basically dx, dy, dz, right? So now I can split the integral into two parts. One is my first, valence to conduction band, which is going to be, let's say mCv, that is going to be having some coefficients. I'll ignore them, some coefficient c. And then the envelope function, the final state is going to be my conduction band. So uc star of r. And let's say I'm assuming for a moment, x direction is my electric field. And then uv of r dx dy. This is the one part of the integral. And then there's going to be another integral which is going to be m n n prime, I'll call it, which is going to be again some overlap, something. Or I can put all the coefficients in the first integral, so we can ignore this. So this is going to be phi n z, phi n prime z dz. There are two parts. So product of this is essentially this. That's it. Integral I'm just separating onto two parts. Okay. The reason we are doing that is this is basically what we call as electron and hole overlap. Electron hole overlap integral. And this is my valence band to conduction band dipole moment. Dipole moment integral, right? Integral of the dipole moment times the wave functions. So if you do that, there's an expectation value that comes out. Yeah. There's a question I have here. Yeah. Mm-hmm. Mm-hmm. Okay. So the question was, there is an x term here in the MCV, but in the MNN prime, you don't have. Okay, sorry. I should actually written it. I'm sorry. I should. But the previous case I said it is MVC, valence band to conduction band. All right. So yeah. Anyway, it doesn't. So there is an x term here, but there's no x term here. Why? The reason for that is I'm assuming that the electric field is only in the x direction. That's why I wrote it. But suppose I consider a case where the electric field is in the z direction. Okay. Then I'll have to look at this. Does that answer the question? No, okay. The question is, how will the electric field be in the z direction? Right? So the question is, okay, so I can think of, let's say, a quantum well, which is, let's say, gallium arsenide like this. And then I have bigger pieces of aluminum gallium arsenide. Okay, so the quantum well is, this is a z direction, let's say. This is my z direction, right? Now my electric field has to be in the z direction. So for that, I have to have a plane wave which is incident in this direction from the side. If I have such a scenario, or if I'm thinking of, let's say, an emission from a laser, okay, I'll have this sort of a behavior wherein my electric field is confined and back and forth, it's going in this direction. And now the electric field is in the z direction, right? So now I have to, of course, take that also into account. It becomes important. This kind of an interpretation now where x direction it is there, that means I'm actually considering incidence from the top. In that case, I'll have only x and y components of electric field. But if I'm considering a side incidence from the side, then I'll even have z component. Then we'll have to actually consider that as well. So one important effect, okay, thank you. So basically what, if I look at the matrix element notation, this notation, where initial state and final state, and let's say if I have electric field in various directions, right, x, y, z. So the important thing to remember, in this case, final x, let's say electric field is in the x direction. This matrix element, because it's confinement in the x and y, electron can move about in the x and y direction. X, y, this is going to be equal, but this is not going to be equal to final state z. If my electric field is in the z direction, there is going to be an anisotropy that comes in because we have confined the electrons in the z direction. All right. So that's going to happen. All right. So now, what does the meaning of this overlap integral? Okay. If you looked at m n n prime, right, is this overlap integral? It's simply going to be, overlap is phi z, right? Phi z is the the wave function for a particle in a box. Sine of n pi by L z times sine n prime pi L z dz. Okay. So, I mean, if you look at the math and you just verify for n equal to 1, 2, 3 and so on, you will see that this integral turns out to be 0 for all n not equal to n prime. And it is only going to be some finite number for n equal to n prime. So what this means is, if you have a quantum well and you have, let's say, a potential well like this, okay, I'm just amplifying the barriers. So each of them is going to be having some discrete levels, okay. So there's going to be n equal to 1, n equal to 2, similarly n equal to 1, n equal to 2. Remember, holes, the energy increases as you go down, okay. That's why n equal to 1, 2 and so on for holes. For electrons, n equal to 1, 2 and goes up higher. Excuse me. So what the overlap integral m and n prime equal to 0 or not, it implies is you can have electrons making a transition only when, like only in the case of, let's say here, from here to here, from here to here, okay. So this is going to be E1 to 1 transition, okay. This is going to be n equal to 2 to n prime equal to 2. Sorry, I should have written that. And if I call this as n prime, right? 2 to 2 transition. And similarly, you can have E1 to 1 transition. But you can't have a transition of this form. E2 to 1 transition is not allowed. Okay. So absorption or emission can take place only for delta n equal to 0. The change in the quantum number from the valence to conduction band can only be 0. It has to occur between the states which are same, having the same quantum level. All right. So this is an important observation, because in principle I can compute, right? I can compute if I give you the confinements, you know what is a EG, and there is this, you might say for electrons I can, okay. So now if I confine my energy E, right, is going to be EG plus delta E associated with the electrons, right? Or I can call it in my language here with the conduction band, I can call it n prime E n prime, right? That is associated with the conduction band plus delta E n, which is associated with the holes in the p type, right? Sorry, in the valence band. So because of that, the effective masses are different. The energies need not be equal. Delta n and delta n prime need not be delta E. Sorry, these two quantities, delta E n prime and delta E n, need not be equal, because effective masses are different. There is an m, right, in the denominator. The effective masses are m. E is not equal to m h. Whole effective mass is not same as the electron effective mass, so there is some difference. So because of that, the exact transitions are a little bit tricky, but we can compute them, and it turns out that these are exactly verified using experiments. So they're true, but it has a little bit of a nuance associated with that. All right. So that's why we need to know this. So is that okay? Make sense? All right. So this is important when we are working with quantum wells. Let's say, there is this directionality, there's a polarization dependence that comes in. Polarization is basically the electric field direction. So, electric field in X and Y and Z is going to be different. All right. All right. So let's go back now to the original question that I asked at the beginning of the lecture. Can we have a transition, let's say from energy level 1 to 2? Okay. So can I have a transition like that? Okay, is it possible to have E1 to E2 transition and E1 to E3 transition? Let's check. Okay, so now I'm considering basically a potential well, a simple potential well, 1D potential well. I'm even removing the X and Y component. So I'm just, electron is confined in the 1D, electric field also is in the 1D, let's assume. Okay, so what essentially I need to find out is, now I know my wave functions, right? What does my overlap integral, what does my, Fermi's golden rule, the dipole moment tell us? So not the dipole moment, the matrix element tell us. So psi f x psi I dx. In this case, that is going to be, my final state is going to be psi 2 of x, x psi 1 of x dx. And I know my wave functions, right? Because wave function psi n is going to be sine n pi by Lx. So I have this. So what I can do is I can try to compute this integral graphically, and that's what I have shown here. So basically you can have a scenario wherein, let's say this is my potential well. You have the first wave function which is like this, okay, similar to this blue here. And the second level is basically a wave function which goes like this, okay, which is going like this, okay. So, and then I have an x which is basically an odd function like this. Now my integration of psi f x psi I is simply going to be a product of these three things integrated, right? So if I take a product of all these three things, I get what is shown here on the in the pink here. Basically, there is here this area under the curve here and the area under the curve. And if you look at the areas under the curve, this is pink is a product of blue, red, and black. All right. So if you have this, so basically the area under the curve is non-zero, right? So basically this area under the curve is non-zero. Therefore, this is an allowed transition. But let us consider the second case where I go from 1 to 3 level. Okay. If I do this, then my wave function is going to be psi 3 of x, x psi 1 of x dx. Okay. So I have my initial wave function which is still the blue, but now my green is essentially the wave function for the third state. So you have this sort of a dependence. So if you see here, this is dependence. When you have such a scenario, and then you have this odd function which is x, right? You take a product of it and you end up with a pink line. But now what happens is you have this negative sum here, positive sum here, negative sum here, positive sum here. So what happens is the positive and the negative cancel out. Similarly, the positive and negative cancel out. The overall integral is an odd function and overall product is an odd function. Because of that, this is always going to be 0. So transition not allowed. Okay. So that's why it turns out that whenever you have delta n, for a 1D case, if you have delta n to be even, this is forbidden. The change in the quantum numbers, n equal to 1 to n equal to 3, the delta n is even, that is forbidden, and delta n is odd is allowed. Okay. So a question arises, if delta n equal to 1 is allowed, can I odd allowed, right? So I'll definitely have a transition from equal to 1 to equal to 2. Can I have a transition from equal to 1 to equal to 4? Yes, right? Delta n is odd. Does it have the same amount of absorption? For that, we have to compute the integral. So you see here immediately, if for that, you have to compute the amount of integral, and that's going to be some number. Okay. But we have to see what it is. And that's what I have done here. Okay. So what we have done in this case is, you remember the matrix element is simply integral of psi, let's call it n prime, x psi n dx, right? So basically you're considering pairs of states, n equal to 1, 2, 3, 4, 5, and n equal to 1, 2, 3, n prime equal to 1, 2, 3, 4, 5. Okay. So now we computed that integral and we put it in a matrix in this form. So basically, if I take, this is my, let's say n, and this is my n prime. this axis. Okay, this is my n axis. So can I go from n equal to 1 to n prime equal to 1? The change is initial state to final state. There's no change. I mean, there's no transition at all. The energy, there's no change, right? But it can go from n equal to 1 to the final state of 2. Okay, let me not use the notation of n prime and n because that might be confusing. Let me simply say that this is my final state, psi f, and this is my initial state, psi I. Okay, initial to final, if I go from first state to second state, delta n equal to 1. So it is allowed. It's an odd number, but you see that the magnitude is now 0.5. Okay, it's allowed transition. But next one, if you go from initial first state to third state, the delta n is 2. It is not allowed, so it is 0. But then you go from first state to fourth state. It is allowed transition, but the number is smaller. Okay, so if you look at the ratios of these, if I look at E 1 to 4, or rather I'll write it 1 to 2 divided by E 1 to 4. This is going to be 0.55 divided by 0.04, let's say. So how much? 12 times? Roughly? 12 times. Okay. So the 1-2 transition is 12 times stronger. Absorption is very strong. Similarly, if you go to higher levels, of course, energetically they are allowed. Momentum conservation, we don't need to worry. But still the amount of absorption is going to be different. Okay. And that's what you see here. And similarly, I can even think of, I can go from, second level to come down to emit to first level. So that is also going to be allowed. The same number is there. These two are identical because if I go emission or absorption, that's going to be the same thing. Okay. And you see that similar trends are absorbed. And essentially what you have is there is a matrix that we can generate out of this for various states. And that's why we call it matrix element. All right. And this plays a very significant role. You might say, why are you going into all these arcane details? Well, these arcane details are what are, important for operation of laser diodes and LEDs and so on. And if you want to look at the spectrum and understand them deeply, you have to go into all these details. That's why I'm doing this. All right. Okay. So I did one more thing. I mean, this is a very simple code that I think I will put it up on GitHub. Or you can write to me if you're interested and I can share it with you. We have a simple Python notebook for this. And you can look at it and try to do it yourself. We did one more thing. We said, what happens when you increase the width of the potential well? Okay. So far, when I talked about this matrix element, I didn't put in any number, right? I mean, of course, this is going to be 0 to, let's say, L, right? The integral is going to be from 0 to L. So what happens if I increase that? So initially I took a width of okay, this is an arbitrary thing. Width is equal to 3 and width equal to 6. What happens to the matrix elements? And immediately you see that, of course, this width is going to be rough. It's going to increase. Okay. So the similar trends you will see here. You have n equal to odd allowed. Delta n equal to odd is allowed. Delta n equal to even is not allowed. I can put it in right here. This is not allowed. Right. So yeah, this is again odd. So you see this is allowed. All right. And if you go to very high levels, the strength weakens. A similar trend happens. Okay. So if the width of the potential well increases, the matrix element becomes bigger, implying absorption is stronger. Okay. So you might say, well, all these are simple, toy problem, right? Particle in a box. Is it true? Well, it turns out that people have done experiments. In this case, they have looked at optical absorption in molecular chains. So, this is basically a molecule with chemical molecule with, let's say this is, I think it should amine group. So nitrogen is there is an amine. This is methyl group attached to nitrogen. And then there are these ethyl groups in the center, NH, NH, and so on. This K represents, how many times you can repeat. Essentially, it turns out that you can change the length of the molecule, okay? And then you can put another comma, and there's an amine group on the other side. So effectively, the electron is now confined to this chain length, and the amine groups acts as a barrier on both sides. So electron is confined to this. So effectively, if you have the particle in a box problem, you had this infinite potential. But it turns out that if you have a molecule like this, it sort of mimics, the potential. It looks like this realistically in this molecule. Now electron is confined to that. Now you can think of changing, this basically this entire unit here, CH, there's a K. Basically you can change the K. You can repeat n number of times, K equal to 1, 2, 3 and so on. So if you take K equal to 1, we have, so let's say one dimolecule with, 1, K equal to 1. So basically CH, 3 carbon atoms are there in this, okay? If you take K equal to 2, basically there are 2 of these. So CH, twice, CH, and then CH. So 5 carbon atoms and 7 carbon atoms. So essentially we are changing the length of this chain, okay? How will the absorption spectrum look like? All right. If you look at it, the absorption first die, second die has 5 carbon atoms, third die has 7 carbon atoms. So as you make my quantum well larger, L equal to, as L increases, right? Because the length of the chain is increasing, the absorption A is redshifted. Why is it redshifted? Well, the energy En is going to be n square pi square h cross square divided by 2m L square. If L increases, you can compute what is, the transition energy, and you will see that that's getting redshifted. The energy levels become closer and closer. So energy reduces, so the wavelength increases. So that's why they're getting redshifted. Okay. And then the intensity, the amount of absorption, right? The coefficient also has increased. Okay. The reason coefficient has increased is that the matrix element is larger now. It's easier to absorb. Okay. So this is an additional constraint that we have for optical absorption. To explain these experimental data, we have to do this, okay? So I'm sorry for the figure. This is not the highest quality, but I took it from this book directly. So you can go back and look at this for more details. But effectively you can understand why the absorption increases. Any questions about this? Well, this is actually made in solution. You have the dimolecule, there is some concentration, some molar concentration, and then per centimeter cube. So they have normalized everything, and still you see that there is this increase in the absorption that happens because of the quantum confinement. All right. So you see, it's a very, very important thing. All right. So we talked about bulk, then we introduced 2D, then we talked about 1D. The last thing I want to leave you with is quantum dot, a zero-dimensional, semiconductor. Okay. Now you can make actually these quantum dots out of various materials, from zinc oxide, cadmium sulfide, cadmium selenide, telluride, and so on. And each of them have different amounts of band gap. And you see that they exhibit this band gap. Energy associated with that is this. But the moment you make the size smaller and smaller, you see this increase in the band gap energy. Okay. That means the emission is going to get blue shifted. And that's what you see here. This is, if you want to have an emission in the IR or, in the red part of the spectrum, use selenide. But if you want it in the blue part of the spectrum, you need to use zinc selenide and so on. So various materials are available for us. And these materials are what give us these lustrous colors that we see from quantum dot solutions. In principle, actually, it is possible to incorporate this into glasses, and you have these bright glasses which can act as a filter. They're very, very sharp absorption peaks. They can act as a filter, and they can, they can be used in TVs now. You excite this, you have very nice bright colored TVs that can come out of it. Okay, I believe Samsung has a product in this, wherein they have a quantum dots which are in the part of the screen, and you excite them. Depending on which pixel you excite, that color comes out. Okay. So a lot of these applications are in the market already. And so, with that, I hope that I have convinced you that the semiconductors and the confined semiconductors have a very, very important role to play in nanophotonics. All right. So if you have any questions? Okay. Since there are no questions, we'll stop here. In the next week, we'll talk about plasmonics. So far, we have looked at basics, the material properties. Next week, we'll actually talk about what happens, how does a metal interact with light. All right. That's going to be interesting. We'll actually talk about resonances that occur, which are called as plasmonic resonances. And then after that, we'll move to the dielectric structures again. All right. Thank you so much for your attention. We'll see you in the next week. Bye.